Sometimes we have to use implicit differentiation to find a higher order derivative. And this isn't necessarily more difficult, but it is substantially more tedious than just using implicit differentiation for a first order derivative. So in this first example, we are asked to find the second derivative of y with respect to x in terms of y if y cubed minus 4x equals 3. So again, I really have to use implicit differentiation here, as I can't isolate y. So when we find our first derivative, again, we're starting with our power rule. So we would get like 3y squared times y prime or times dy dx, whatever you feel most comfortable with writing there. I'm going back to dy dx on this one. All right, so that's our derivative of y cubed. And then when we get to our second term, minus 4x, well, the derivative of that with respect to x is just negative 4, or I could think of that as minus positive 4. And then again, I'm really taking the derivative of both sides of this entire equation. So on the right-hand side, this is going to be equal to 0. Okay, so this one actually wasn't so bad. So we could rewrite our derivative here if I wanted to. Like I could add 4 to the right-hand side and divide by 3y squared. So I could isolate and say, in fact, we probably do want to do this, and say that dy dx is equal to 4 divided by 3y squared. So again, we added 4 to both sides, divided by 3y squared. Okay, this first derivative wasn't terrible because we didn't have to use the product rule. All right, so now we want to take our second derivative. So as we do, when we take our second derivative, it's the derivative of our first derivative. So now when we take the derivative with respect to x on the left-hand side, that's what becomes our second derivative of y with respect to x. And then we have to do so on the right-hand side as well. So I need to use the quotient rule here because we have division. We have a quotient of 4 divided by 3y squared. All right, so when we take our derivative, we're going to multiply 3y squared with the derivative of our numerator. Well, the derivative of our numerator is just 0. Times minus 4 times the derivative of our denominator. So that's going to become 6y dy dx all of that over our denominator squared. All right, so we get our second derivative. Well, we said this term becomes 0. So when I multiply this out, I have negative 4 times 6, so negative 24y times dy dx over 3y squared to the second power is going to be 9y to the fourth power. And there's something else we're going to have to do here, but what we might want to do is we actually can simplify this, right? So like 24 and 9 have common factors. We also have a factor of y and 4 factors of y in our denominator, 1 factor in our numerator. So I could go ahead and simplify this at first by dividing out a 3y. So I could think of this as like 3y times negative 8 dy dx over like 3y times 3y cubed. All right, so we end up getting negative 8 dy dx over 3y cubed. But here's the thing, we're not done yet, because if we go back and read how we're asked to do this problem, we are asked to find the second derivative in terms of y. And what we can infer from that is that means we should not have dy dx in our derivative. we should only have the variable y in our derivative. So if we go back to our first derivative, we already know, I know that I kind of wrote over it, but we knew that dy dx is equal to 4 divided by 3y squared. So I could substitute that in for dy dx into my derivative here. I realize that I'm not making good use of my page here. I'm writing off the page and I left a bunch of blank space. So do as I say, not as I do. All right, so we get negative 8 times 4 over 3y squared divided by 3y cubed. And again, to clean that up, we probably don't want a fraction in a fraction. So I might multiply both the top and bottom of my big fraction by 3y squared. That'll clean up that divided by 3y squared on top. So we get negative 8 times 4, so negative 32 over 9y to the 5th power there. All right, that was a lot of work, but that is our second derivative in terms of y, written way to the side of my OneNote there. Sorry about that. I should have just started on the left. All right, for that second example, similar thing here. We're doing the same thing, but it's for the curve defined as x squared plus y squared equals 4. I'll try to make better use of my space for this example. All right. So again, we're going to start off with taking the derivative of x squared plus y squared equals 4. So I get 2x from my first term plus 2y, y prime, or dy dx, whatever you feel better about, for my second term. And again, that's going to equal 0 because we're taking the derivative of both sides of this equation with respect to x. And so now we want to go ahead and isolate our y prime. So we could subtract our 2x from both sides, and then we could divide. And notice we only have one term on the left. There's only one term with a factor of y prime, so it's easier when we go to divide. There's nothing to factor out over there. And finally, we could go ahead and cancel out those 2's. So we get negative x over y, or just negative xy. So that is our y prime. So now we're asked to find the second derivative. So when we go to find our second derivative, just like before, we're taking the derivative of y prime. So our second derivative, again, I'm going to have to use the quotient rule here because negative xy is a quotient. And we can keep the negative out front, or we could assign the negative to the numerator or the denominator. And I'm just going to tell you something that helps me not make a mistake when I do this with the quotient rule is I like to assign the negative to the numerator. So I'm going to think of this as negative x divided by y, but you know that's the same as x divided by negative y, or just negative xy. This is just going to help me not make a sign mistake. All right, so again, we're finding our derivative. We're using our quotient rule. So if you're thinking of this as low-d high, we've got y times the derivative of negative x. So that would be negative 1 minus high d low. So that's negative x times dy dx, or y prime. All of that over low r y squared. And so as we clean up our signs, that's a negative y plus xy prime over y squared. And notice I cannot factor out a y here because not in my numerator I have one term that has a y and the other term has a y prime. So I cannot factor and cancel a y because y prime and y are not the same thing. So going back to our prompt again, we were asked to find the second derivative in terms of y. So that means that I should not have an x or a y really in my derivative. So when I go back, if I look at my first derivative, I could go ahead and substitute that into this expression for our dy dx. And this one's going to be a little tricky. This is one that I sometimes have to think on. But where I see my y prime, I'm going to substitute negative x over y. So I'm going to do this in a different color. So we get negative y plus x times, think of this as negative x over y. It doesn't matter if I think of that whole thing being negative or assign it to the numerator or denominator. And this is over y squared. And so right now, I still have x's in my derivative. And there's a couple orders in which I could think about this, but that divided by y piece is really bothering me. So I might want to go ahead and kind of eliminate the fraction within my fraction. If I do that, I have to be really careful. When we did that above, we didn't have multiple terms in our numerator. So if we do that now, we're going to have to distribute y on top to both terms of my numerator and multiply by a y on bottom. So when we do that, we're going to get negative y squared, because that's negative y times positive y, plus, although it's going to be negative, negative x squared over y cubed. And so, okay, we still have x's and y's in our numerator. But what I'm starting to notice is that my numerator is actually kind of starting to look like the curve I started with, but we do have some negatives to deal with. So what if we factored out a negative 1? So I'm still working with my second derivative. But what if I factored out a negative 1 from my numerator? I could now write this as y squared plus x squared, which is the same as x squared plus y squared over y cubed. And then if I think about it, the curve that I'm working with is defined where x squared plus y squared is always 4. So if this is the second derivative of that curve, x squared plus y squared is always the number 4. So we end up getting negative 4 over y cubed. So there might be some different ways that we could have gotten to that second derivative, but that one can be really tricky. But there is a way that we can rewrite that in terms of y. All right, our very last example. I would encourage you on this one to pause the video and try this example and then come back and check it. All right, so we're finding the second derivative evaluated at the ordered pair 0, 0, so when x and y are both 0, for the sine of y equals x squared. So we need to find the derivative with respect to x, the second derivative of the implicit relation sine of y equals x squared. So when we find our first derivative, we're taking the derivative of the sine of y. And so I know the derivative of sine of some junk is cosine of some junk. So I get cosine of y. But since my junk isn't an x, I'm going to pick up a dy dx or a y prime. So again, that's just implicit, or when we use implicit differentiation, it's really just the chain rule. All right, so cosine of the junk times the derivative of the junk. All right, on the right-hand side, our derivative of x squared with respect to x is just 2x. All right, so to isolate y prime, I could divide both sides by the cosine of y. So my first derivative, dy dx or y prime, I could write as 2x divided by the cosine of y. And I'm going to point out that that's the same as 2x times the secant of y. So now we have to find the second derivative. But we have a couple options. The option is, do I want to use the quotient rule with 2x and cosine y? Or do I want to use the product rule with 2x and the secant of y? And either way should work. Like, we should get the correct answer either way. Our work in between might look a little bit different. And so I'm going to tell you my personal preference is the product rule over the quotient rule. But you are welcome to try something different, and we should get the same thing. All right, so I'm going to use this form of our first derivative. So when we go to find our second derivative, I'm going to use the product rule between 2x and secant of y. So the derivative of my first factor times my second is just 2 secant of y, plus the derivative of my second factor times my first. Well, I know the secant of some junk, its derivative is secant of the junk times tangent of the junk times the derivative of the junk. That last part's the chain rule. So I'm going to get secant of y times tangent of y times y prime, or dy dx, and then I still have to multiply that with my 2x from the first part of the from the product rule. Okay, this is looking a little icky here. Now we can clean this up, but I want to kind of go back to what our prompt is asking us to do. It's asking us to evaluate our second derivative for when x equals 0 and when y equals 0. So that means, like, everywhere I see an x, so, well, just right here, I'm going to plug in a 0. And everywhere where I see a y, not a y prime, but a y, I'm going to plug in a 0. So the only thing that is still like our variable here is dy dx at 0, 0. So we could go ahead and substitute 2x secant of y. Like, we could substitute this for dy dx in our expression here, and that would be just fine. But alternately, because we know we're evaluating this derivative for when x and y are both 0, we could just evaluate dy dx for 0, 0. So out to the side, I'm going to evaluate my first derivative at the ordered pair 0, 0, and I need to use this notation to show that's what I'm doing. And I'm going to get 2 times 0 times the secant of 0. And the secant of 0, I know, is 1 over the cosine of 0. And since the cosine of 0 is 1, the secant of 0 is also 1. But it doesn't matter if I know that in this particular moment because I'm multiplying that by a 0. So dy dx is 0. And when we do that, we can actually see this is going to save us a lot of time evaluating our second derivative here. Because now, when we substitute 0 for x and 0 for y, we have 2 times the secant of 0 plus the secant of 0 times the tangent of 0 times, well, we just found out dy dx at the ordered pair 0, 0 is 0. So times 0 times 2 times 0, this entire term is just 0. So our second derivative is 2 times the secant of 0, which is 2 times 1, which is just the number 2. So if we read the prompt carefully, and if we're asked to evaluate our second derivative at a particular point, we can save ourselves some time by just plugging in the values we know. We didn't really need to clean up our second derivative. However, if we were to see the language that might say, like, find the second derivative of y with respect to x, generally that means we are expected to clean up our derivative and possibly, like, if we're doing it in terms of x and y, that's when we would want to substitute 2x secant of y for dy dx. So we just have to read the directions really carefully.